Chapter 5 is about gases. In Chapter 1, we learned about the three phases of matter. We have solid, liquid, and gas. And solids have a unique shape and volume, where liquids have a unique volume but take the shape of their container, and gases take the shape and volume of their container. Gas molecules are fast-moving and far apart from each other. A gas always occupies all of its container, so it takes both the shape and volume of the container, as illustrated below. The volume of a gas is how much space that gas occupies. Most gases are clear, so if I was to take that clear gas and put it into a container, it's hard to visualize it taking the shape and volume of that container. Here I have an example of two colored gases. On the left, I have bromine, which is a reddish-brown gas. On the right, I have NO2, which is a brown gas. As a review, let's name NO2. First, determine is this an ionic or covalent compound. So nitrogen is a nonmetal, and oxygen is also a nonmetal. So two nonmetals make a covalent compound. And to name covalent compounds, those are the ones that have the prefixes. So we name the first element N as just nitrogen. And the second element is oxygen, but for the second element, we always change the ending to "ide." So that would be oxide. And then you put those prefixes to tell you how many atoms you have of each element. We only have one nitrogen, but since it's the first element, we don't have to show mono in the front as a prefix. The second one for oxide, we would write di. So this is nitrogen dioxide. Nitrogen dioxide is a compound in smog, which is something we often see in the Los Angeles area, that we have brown skies. So this would be due to NO2. We can measure the pressure of a gas. Pressure is defined as force divided by area. Atmospheric pressure is the amount of force applied by atmospheric molecules on the surface of the Earth. Average atmospheric pressure at sea level is defined as 1 atmosphere, which is abbreviated as ATM. This is a definition I want you to remember. 1 ATM is the pressure at sea level for atmospheric pressure. If we were to go to Mount Olympus in Greece, would you expect the atmospheric pressure to be less than or greater than sea level? If we look at the picture below, there are less atmospheric molecules applying force to the surface of the Earth. So we would expect atmospheric pressure in the mountains to be less than atmospheric pressure at sea level. And at Mount Olympus in Greece, atmospheric pressure is 0.695 ATMs. So that's much smaller than atmospheric pressure at sea level. The same would apply as if I was to go below sea level. Would you expect atmospheric pressure to be greater or less? This one's going to be greater because you'll have more molecules applying force, and you also have the pressure of that water. So that's going to be much greater. So what I want you to remember is atmospheric pressure at sea level is 1 ATM, and be able to compare if you are at a higher elevation than sea level, is atmospheric pressure greater or less, and if you're below sea level. Barometer is a device to measure atmospheric pressure. The barometer was invented by Evangelista Torricelli in 1643, who was a student of Galileo. A barometer measures the height of a liquid pushed up in a sealed tube by atmospheric pressure. So if we look at the example here on the right, we have mercury in this open container. And then we have this inverted glass tube in the mercury. Now we can imagine I have my atmospheric molecules pushing down on the surface of the mercury. They are causing the mercury to travel up the tube. If we are at sea level, the height that those atmospheric molecules will push mercury up the inverted tube is 760 millimeters. So I do want you to remember that definition as well. So at sea level, atmospheric pressure can also be defined as 760 millimeters. If I was to have water inside my tub here, water would go up a sealed tube up to 10.3 meters. You don't need to remember that, but just to show you why we use mercury instead of water. So you can imagine the height here. 760 millimeters is about 3/4 of a meter high. And 10.3 meters is very tall. So that's going to be, 10 times higher than this. You need an extremely tall glass tube. Different units you can use to measure gas pressure. There are 3 that I want you to be familiar with. ATM for atmospheres, mmHg for millimeters of mercury, and torr, which is given in honor of Torricelli, who invented the barometer. I also want you to know how they're equivalent to each other. So we said at sea level, atmospheric pressure is defined as 1 ATM. And then we looked at the barometer, and you have a dish of mercury that atmospheric molecules push the mercury up that inverted tube a distance of 760 millimeters. So we can say 1 ATM is equal to 760 millimeters. So I do want you to remember that. Now 1 ATM is equal to 760 torr. Or we could say 1 millimeter of mercury is equal to 1 torr. So therefore, 760 millimeters of mercury is the same as 760 torr, which is equivalent to 1 ATM. So these are the 3 atmospheric pressure units I want you to be familiar with. And then how to convert. When we have equalities, we can create a conversion factor. So for example, if I asked you to convert 0.695 ATMs to millimeters of mercury, we could create a conversion factor. So 1 ATM is equal to 760 millimeters of mercury. We could set that up in the fraction format by saying 1 ATM divided by 760 millimeters of mercury, or 760 millimeters of mercury divided by 1 ATM, because they're equivalent to each other. So let's go ahead and set up our problem. We always start with what's given. We have 0.695 ATMs, and we're going to pick the conversion factor to cancel our units. So the one on the right, we have 1 ATM at the bottom, which will cancel our units, and 760 millimeters of mercury at the top. So 1 ATM cancels the ATM from the given units, and we'll end up with millimeters of mercury. So then if we multiply 0.695 times 760, we get an answer of 528 millimeters of mercury. A manometer is a device to measure the pressure of a gas in a closed container, as illustrated below. This is our container. The gas would be inserted into this container, and we have a U-tube attached to our container with the gas in it, and the U-tube contains mercury. We can measure the pressure of the gas by comparing the atmospheric pressure that is pushing down on one side of the mercury in the U-tube and calculating the difference from the pressure of the gas being applied to the mercury on the other side of the U-tube. And then we could calculate the pressure of our gas. Manometers may be used in measuring blood pressure, as shown in this photo. The manometer reads the air in the blood pressure cuff, which is the applied pressure that matches the blood pressure. Mercury is used in manometers and it's also used in barometers. Mercury vapors are actually toxic. So I'm going to tell you a story about the Mad Hatter. You may have heard of him in Alice in Wonderland and the quote-unquote mad, where that came from. So in the olden days, the Hatters used to use mercury to make rabbit hair soft, and then they took that rabbit hair and they made it into felt, which they used for making hats. In the process, they inhaled the mercury vapors, which caused their teeth to fall out and caused nervous disorder where they were twitching, and also they acted a little bit crazy, which is where the term mad came from. The behavior and property of gases can be explained by the kinetic molecular theory. I have written the letters SMEC, we call that SMEC, to help you remember the 4 points of the kinetic molecular theory, which I would like you to remember. The first, the S, stands for space. So the first thing to remember in the kinetic molecular theory are gases are mostly empty space. The size of a gas molecule is so small compared to the space around it, we consider it minuscule. So we don't account for that volume of an atom or a molecule in our gas. We consider the volume of the container equal to the volume of a gas, as shown down here. You can see the gas molecules moving around. This diagram shows them. They're looking pretty large, but they're really much, much smaller than that. So as an example, if I had 1 can of soda in the liquid phase, and I looked at all the molecules in there, and I converted that to the gas phase, the volume it would take up would be equivalent to 1,700 cans of soda. So that's an idea to give you how small these molecules are, of how much space they would take up. So just remember, gases are mostly empty space. The second point of the kinetic molecular theory is gases are in continual random motion. So the M is in the SMEC, SMEC. So the gas molecules are moving in all directions at very high speeds, which cause them to fill up the entire volume of a container, which is illustrated in this container of our gas below. The third point of the kinetic molecular theory is gases have a certain kinetic energy, which is the energy of motion. So to help you remember kinetic, if you think of the term kinesiology, which is the study of motion. So for example, when I went to take a yoga class at Pierce, I couldn't find it under physical education. All of our physical ed classes are under kinesiology. So gases have a certain kinetic energy, which is the energy of motion. This energy is proportional to temperature. So think about if you're standing there and a fire is behind you. You're increasing the temperature. Is that going to make you move faster or slower? You might want to speed up to get away from that. So increasing temperature increases kinetic energy. And in our term SMEC, we're looking at E for energy. The fourth point of the kinetic molecular theory is gas molecules elastically collide with each other. So when I say the term elastically, that means the gas molecules hit each other, like in our diagram right here, and they bounce apart. You can think of an analogy as if you were playing pool and your pool balls hit each other, they bounce right apart from each other. That's the same what happens with our gas molecules. And the gas molecules, they can collide with each other and they can collide with the walls of the container, as this one is showing you right here. When the gas molecules collide with the walls of the container, that results in pressure. So for the fourth point, remember C in SMEC stands for collisions, and these collisions result in increase in pressure. Now, if you think about sometimes on hot days, you may have seen people on the side of the road with flat tires. This can be due to, because of the hot weather, you're increasing the motion of those molecules. So by increasing temperature, you're going to end up increasing the pressure as well. And you could get to the point where you increase the pressure so much due to that hot day that your container that has the gas in it, like your tire, might explode. Or if maybe you had a gas cylinder, you have to be concerned about the temperature it's stored at, because if it gets too hot, it will explode because of the increase in temperature due to the motion of those gas molecules. So remember the 4 points of the kinetic molecular theory. SMEC, S is space, M is motion, they're in continual motion, E is energy for kinetic energy, and C is collisions. And those gas molecules colliding with their container result in pressure. There are certain properties of gases that we can measure, such as temperature. When we use the gas laws, we'll always measure temperature in Kelvin. We can measure the volume of our gas, the pressure of our gas, and the quantity of a gas. And then we can look at the relationship between these different properties and consider our gas laws. For example, I have here a flat tire on my bicycle. I'm going to add a certain quantity of gas to it. What's going to happen to my volume when I add more gas to it? And that's something you know is going to increase. So that's one of the gas laws that we'll be looking at. Another example would be, let's say we cap our tire once we've put in enough air we want, and then it gets hot out. We can look at the effect of temperature on the volume of the gas. So that's another gas law we'll be looking at. So now we're going to learn some of our gas laws. Boyles' law was developed in the 17th century by Robert Boyles. Boyles' law states the volume of a gas decreases as pressure increases at a constant temperature and for a fixed quantity of gas. He developed this equation, P1 V1 is equal to P2 V2, and again this is at constant temperature, and N is our quantity in moles. So N is the abbreviation for moles. This is not changing. So what P1 stands for is my initial pressure. V1 is my initial volume. P2 is my final pressure, and V2 equals my final volume. So we're looking at the relationship for a fixed quantity of gas, and if we change the pressure, how is the volume going to change? Or if we change the volume, how is the pressure going to change? So in this example below, the first gas sample here we have is at pressure 1 atmosphere. The volume is 1 liter. We're not changing the quantity of the gas. It's got the same number of gas molecules in our second scenario here, and it's occurring at the same temperature. So what we've done is we've increased the pressure. So we went from 1 atmosphere to 2 atmospheres. So by increasing the pressure, we are going to decrease the volume. So we can see our volume went from 1 liter to half a liter. In this example on the right, we have marshmallows in syringes. The syringe on the right has the plunger pushed all the way down, so it has more pressure than the one on the left. We can look at the volume of the marshmallows in here. They're much smaller compared to the one on the right where we have less pressure. The plunger is pulled up. The volume of those marshmallows are much larger. So you could try that at home if you'd like to for fun. But I do want you to know the relationship between pressure and volume and how that changes for a fixed quantity of gas if you increase the pressure for those gases. You don't have to remember the formulas. The formulas will be given to you So the formula P1V1 equals P2V2, I will give that to you for your quizzes and exams. Here is an example of Boyles law in our everyday life, which is breathing. When we inhale, the volume of our lungs increases due to the decrease in pressure. So in this picture below, this is showing breathing in. What happens is your chest expands because the rib cage is moving up. Your diaphragm contracts or moves downward, and this causes a decrease in pressure, which allows the air to come in and have a larger volume for your lungs. When we breathe out, we increase the pressure by having the diaphragm push upwards, and then the lungs or the rib cage push down on the lungs, which increases that pressure, which decreases the volume of our lungs. So this is an example of our everyday life showing the relationship between pressure and volume based on Boyles law. And I do want you to remember the relationship between pressure and volume using Boyles law. Here is a Boyles law example calculation. A person breathes about 20,000 liters of air per day at sea level. We know atmospheric pressure at sea level is 1 atm. How many liters would a person have to breathe on Mount Olympus, where atmospheric pressure is 0.695000, to get the same amount of air? And we're assuming the temperature is the same at sea level and up in the mountains for this example. The first thing you always want to do in any kind of word problem is to write down the information given to you. So our initial pressure is sea level, so that's 1.0000 atmospheres. Our initial volume is 20,000 liters. And my new pressure is 0.69500 atm. The question I'm looking for is how many liters? Liters are our units for volume. So that's my unknown is V2. Now, before we do the calculation, I have a second question here that says, do you expect the volume to increase or decrease? This is where you can kind of think about your answer if it makes sense at the end. So if we are decreasing the pressure, what would happen to the volume? The volume should increase. So let's see what happens with this one. We write our formula, P1V1 is equal to P2V2. And then we plug in the values given. So P1 is 1.000 atmospheres. V1 is 20,000 liters. And that is equal to P2, which is 0.69500 atmospheres, multiplied by V2, which is our unknown. So then we just need to do some basic algebra here. We're going to solve for V2. To isolate V2, we're going to divide both sides by 0.69500 atm. Okay, by doing that, we can cancel out 0.69500 atm on the right side. That will give us V2 by itself. And then if we look at the left, we can cancel the units of atmosphere, and we'll be left with liters, which makes sense for volume. So then doing our math, we have 1 times 20,000 divided by 0.69500, and that gives us a value of 28,776.978 liters for our new volume. So our question was, do you expect the volume to increase or decrease? By decreasing pressure, our volume should increase, which our volume did increase substantially. So now we know the volume of air we'd have to breathe up on Mount Olympus. The last thing you always want to do in any calculation problem is determine the correct amount of sig figs. So the numbers that we were given in our original problem have 6 sig figs. So our final answer should also have 6 sig figs. So let's go ahead and change our number to 28,777.0 liters. A gas has a volume of 2.0 liters at 1.5 atm pressure. What is the pressure in atmospheres if the volume is decreased to 0.60 liters at the same temperature? First thing we're going to do is record the information given. Our initial pressure, P1, is 1.5 atm. Our initial volume, V1, is 2.0 liters. What is the pressure is the question, so P2 is our unknown, and V2 is the volume is decreased to 0.60 liters. Now we can look at the second question. Do you expect the pressure to increase or decrease? So our initial pressure is 1.5. We want to see if that gets smaller or larger. So we can look at our volumes. We started V1 of 2.0 liters. The volume decreased to 0.60 liter. In order to have a decrease in volume, you must increase the pressure. So we can check our final answer and see if it's larger than 1.5 atms. Then we'll give us an idea if we set up the problem correctly. So let's start by writing the formula for Boyles Law. P1 V1 is equal to P2 V2. Then plug in our values. P1 is 1.5 atms. V1 is 2.0 liters. And this is equal to P2, our unknown, multiplied by 0.60 liters for V2. To solve for P2, we need to divide both sides by 0.60 liters. And then we can cancel 0.6 liters on the right. We can cancel the liters on the left. That will give us units ATM, which are the units for pressure. And then we just have to do the math. We have 1.5 times 2 divided by 0.6. I get a value of 5. In order to have 2 sig figs, I'm going to add a 0 to it. So it's 5.0 atm is my final pressure. And let's check if that makes sense. We originally started with 1.5 atms. We expected it to increase. Our pressure did increase. We went up to 5.0 atms, and that makes sense because our volume decreased. Charles' law states that when gas pressure is constant, its volume increases with temperature. Or you could say gases expand when they're heated, as the diagram below shows us. This container at room temperature has the same quantity of gases as the one that's heated, but we can see when we apply heat that the volume has increased. In the 18th century, Jacques Charles developed Charles' law, which states the volume of a gas increases as temperature increases at constant pressure for a fixed quantity of gas. Now, Jacques Charles was a hot air balloonist, so this is how he developed his law, was basically he observed that when the air is heated, the volume of the balloon increased. You can also think about if I have a balloon that's in boiling water, if I decrease the temperature and put the balloon in ice water, the volume will decrease as well. The formula he created for Charles' law is V1 divided by T1 is equal to V2 divided by T2. So V1 is going to be your initial volume, T1 is your initial temperature, and then V2 is final volume, and T2 is final temperature. The volume of a deflated balloon contains 2.0 liters of air at 20 degrees Celsius. What is the volume of the balloon when it is heated to 1,000 degrees Celsius? This occurs at constant pressure and for a fixed quantity of gas. First thing we're going to do is record what's given. So our initial volume is 2.00 liters of air. The initial temperature is 20.00 degrees Celsius. We are going to be heating the air up to 1,000.0 degrees Celsius. And we're trying to find the new volume when we heat it up. So one of the things to remember with the gas laws is the units need to be correct for the different variables. So for example, temperature, the units when you're using the gas laws always need to be into Kelvin. We are given degrees Celsius in this example, so we need to add 273 to find our temperature in the appropriate units. So that would be 293.00 K. And then T2 is 1,000 plus 273 gives me 1,273.0 K. So now that we have the information recorded for V1, T1, and T2, we're going to solve for V2. Let's look at our second question. Do you expect the volume to increase or decrease? So based on Charles' law, it says if our temperature increases, so we're going from 20 degrees Celsius to 1,000 degrees Celsius, the volume should increase. So we can check our answer at the end, again, to make sure that the answer makes sense. So we're going to use Charles' law for this example, which is V1 over T1 is equal to V2 over T2. So V1 is 2.00 liters, T1 is 293.0 K, and then V2 is our unknown, and T2 is 1273.0 K. Now to solve for V2, we're going to multiply both sides by 1273 K in order to cancel our units. So 1273 K on the right cancels, the kelvins cancel on the right, and then we'll have liters for our volume, which makes sense. So then we just have to do the math. So we have 1273 times 2, then divide by 293. And when I do that, I come up with 8.689 liters. And then checking our sig figs, the one with the least amount is 2.00. So that has 3 sig figs. So my final answer needs to have 3. So I'm going to change that to 8.69 liters for my final volume. And based on Charles' law, it says our volume should increase. So we went from 2 liters to 8.69 liters by increasing the temperature. So that makes sense. Gay-Lussac's law is the relationship between pressure and temperature. It states the pressure exerted by a gas is directly related to the Kelvin temperature. In this case, the volume and N are constant. N is equal to moles, which means it is for a fixed quantity of gas. So if we look at our examples here, in the first case, we have a pressure of 1 atm and the temperature is 200 Kelvin. When we increase the pressure to 2 atmospheres, the temperature increased to 400 K. So we have a higher temperature in the second case. The equation is P1 divided by T1 is equal to P2 over T2. Joseph Gay-Lussac developed Gay-Lussac's law, which states the pressure of a gas increases as temperature increases. And this occurs at constant volume, and we could say at a fixed quantity of a gas, which would be our N. The formula is P1 divided by T1 is equal to P2 over T2. And again, the P1 and T1 are your initial pressure and temperature, and your P2, T2 are your final pressure and temperature. An everyday life example would be an autoclave. An autoclave is used to sterilize surgical equipment. This is a picture of an autoclave below, and in the autoclave it has a constant volume. And there's a pan of water at the bottom of the autoclave. And what happens is you can increase the pressure in your autoclave. And as you increase the pressure, the water is going to form steam. So the temperature will increase inside of your autoclave and get to temperatures that are high enough that will kill the microorganisms on your surgical equipment and thus sterilize your equipment. Here are some more everyday life examples using Gay-Lussac's law, which again relates pressure and temperature, and they are directly related. So for example, a pressure cooker, you can increase the pressure and that will increase the temperature high enough to cook your food. A tire is, for example, if the temperature increases, that's going to increase the pressure as well. So previously we stated is if it gets too hot, it might increase the pressure so much that it will explode your tire. You might end up with a flat tire. An aerosol can is the same idea. You can actually explode an aerosol can if you get the temperature too high. A heater as well, you can increase the pressure and that's going to increase your temperature. So again, we have a direct relationship between pressure and temperature for Gay-Lussac's law. The initial steam in an autoclave at constant volume is 100 degrees Celsius at 1 atmosphere. What is the temperature in degrees Celsius in the autoclave after heating the steam to a pressure of 1.15 atm? Let's start by filling in the information given. So our initial pressure is 1.00 atm. Our initial temperature is 100.0 degrees Celsius. And again, for our gas laws, the temperature must be in Kelvin. So we will add 273. So we have 373 Kelvin. Our final pressure is 1.15 atm. We are trying to figure out our new temperature. Now let's look at the question that says, do you expect the temperature to increase or decrease? Gay-Lussac's law said if we increase the pressure, we'll increase the temperature. So we would expect that to increase, and we can check our final answer to see if it's larger than 100 degrees Celsius or 373 K. So our formula for Gay-Lussac's is P1 divided by T1 is equal to P2 divided by T2. So let's plug in our information. So P1 is 1 atmosphere divided by 373 K, and that is equal to P2, 1.15 atmosphere divided by T2, our unknown. In this example, our unknown is at the bottom of a fraction. To solve for T2, it needs to be at the top of the fraction. So in order to get T2 to the top, I'm going to multiply both sides by T2. And by doing that, I can cancel the T2s on the right side of the equal sign. Now I want T2 by itself, so I must do the same thing to both sides of the equation. So I'm going to multiply by 373 K and divide by 1 atmosphere. And I'm doing the same thing on the right as I do on the left. So multiplying by 373 K divided by 1 atmosphere. And you can always check your units to make sure everything cancels. So on the left, we can cancel 373 K with 373 K, and then the 1 atmospheres cancel. So now we have T2 isolated, and on the right, we can cancel ATMs with ATMs, and we'll have a value for temperature in Kelvin. So then we do our math, 1.15 multiplied by 373 and then divided by 1. And when I do that, I end up with Kelvin is equal to 428.95. Now our question was looking for the temperature in degrees Celsius. So we need to convert Kelvin to Celsius. So we will subtract 273. And that will give us an answer of 155.95 degrees Celsius. Then we want to, of course, always check our sig figs in our final answer. The one with the smallest amount is atmospheres, has 3 sig figs. So our final answer should have 3 sig figs. So this would be 156 degrees Celsius for our final temperature. And then we want to check to see does our answer make sense. So we started at 100 degrees Celsius. We increased to 156 degrees Celsius based on increasing the pressure. So yes, that makes sense. The 3 gas laws we have covered so far are Boyles, Charles, and Gay-Lussac's. These are all for a fixed quantity of gas. So the constants for the formulas are expressed in the right-hand column. We can add N, which stands for moles, as a constant for all of these as well. So Boyles' law is the relationship between pressure and volume, initial and final. Charles' law is the relationship between volume and temperature, again the initial and then the final. And Gay-Lussac's is the relationship between pressure and temperature, initial and final, with a constant volume. I also want to mention the units that we've used in our previous problems. The units for pressure were in atmospheres. The units for volume were in liters, and temperature was Kelvin. And also we can look at these relationship and we can see Boyles' law is an indirect relationship. So we learned as our pressure increases, our volume will decrease. Charles' law is direct. As you increase temperature, your volume will increase. Gay-Lussac's is also direct. If you increase the pressure, the volume will increase. Which gas law is represented by this gas law? If we look at this cartoon, we have different pressures being applied by the masses of these 3 different gentlemen. So we're looking at increasing pressure. What happens to the volume? So our volumes, you can see here, are decreasing. So we have the relationship between pressure and volume. Increasing pressure decreases the volume. So this one relates Boyles' law. The combined gas law is the combination of the 3 gas laws we just learned. This is the formula for your combined gas law. I'm going to rewrite it here so it's a little easier to see the fraction format instead of the diagonal line. So it's P1 times V1 divided by T1, P2 times V2 divided by T2. So the 3 gas laws we learned were, first we had Boyles, which was P1 V1 is equal to P2 V2. And then we had Charles, which was V1 over T1 equal to V2 over T2. And then we had Gay-Lussac's, which is P1 over T1 is equal to P2 over T2. So if we look at our 3 formulas, we can find those in our combined gas law. So the first one, Boyles' law, is P1 times V1 equals P2 times V2. And then we have Charles, the relationship between our volume and our temperature, V1 over T1 and V2 over T2. And then lastly, we have Gay-Lussac's, which is the pressure-temperature relationship. And all 3 of these formulas put together gives us the combined gas law. A gas has a volume of 0.400 liters and 4.00 atms of pressure at negative 73 degrees Celsius. what will its volume be at 27 degrees Celsius and 2 atmospheres? First thing always is to write down the information you're given. So we're going to start with V1 is equal to 0.400 liters, and P1 is 4.00 atms, and then T1 is negative 73 degrees Celsius, which needs to be converted to Kelvin. So we're going to add 273, and we get 200 K. And then we have V2 is what we're looking for. That is our unknown. And T2 is 27 plus 273 gives me 300 K. And P2 is 2 atmospheres. Now, based on the information we're given an initial volume, pressure, and temperature, and a final volume we're looking for, and given a final temperature and pressure. So based on that, we know we're going to use the combined gas law. Now, there's two options you can do. You can take your combined gas law, which is given here, and rearrange it to solve for V2. And that's what this is showing here. So if I want V2 by itself, I'm going to multiply both sides by T2 and multiply both sides by T1 because they're both on the bottom. So once I do that, I end up with this portion here. Now to get V2 by itself, I'm going to divide both sides by the T1 P2, and that would give me the format here. And then I could plug in all my values and solve for V2. Or I could take my original formula given and plug my values into that and then rearrange. So let's go ahead and do that. So with my original formula, I have P1 is 4 atmospheres, and I have V1 0.400 liters divided by T1 200 K, and that is equal to P2, which is 2.0 atmospheres, times V2, what I'm looking for, and divided by T2, which is 300 K. Now I want V2 by itself. To get V2 by itself, I would multiply both sides by 300 K and divide by 2 atmospheres. And then on the right side, you can see our 2 atmospheres cancel, our 300 K cancel, and we get V2 by itself. So on the left-hand side of our equality, we need to cancel Ks. So our kelvins cancel and ATMs cancel, and our units that will be left are liters. So then we just need to do the math. We have 300 times 4 times 0.4, that number divided by 2 divided by 200. And we would come up with 1.2. And the number of sig figs, the least amount given in the problem, is 3. So our final answer needs to have 3. So I'm going to add a 0. So 1.20 liters is my new volume.